Okay, so have we got the sound? Awesome. Okay. Any questions about anything? I'll always ask you at the beginning of class if you have any questions about anything. Doesn't have to be about what we talked about last time.
Can it be, why is it $430 for a light bulb?
Yeah, and then I can say, I don't know. I don't know. You know, that sounds like a procurement scandal to me. It sounds like one of those scandals from the 1970s where they found out they were paying, like, you know, the Defense Department was paying like $11,000 for a new toilet, you know, things like that. People were just bilking the taxpayers because no one was watching. But anyway, okay, so if there are no questions, we can continue talking about stuff. So remember last time we were talking about these really general ideas, you know, what is a signal, what is a system, what kinds of signals are there? There's real valued, continuous time, discrete valued, continuous time, discrete valued, discrete time, blah, blah, blah. I was going through some examples of systems, and these are just really broad examples. They're not the kind of things you're going to need to know the details about, but just to give you an idea of the complexity of what can arise in the real world and that these things are part of your daily life. Okay, so we talked about in super general, and today we're going to start getting more mathy, so, but let me just finish this part first about signals. And these are signals of various kinds. And at the end of class, we were talking about systems. And remember what a system is. A system is just an entity that processes input signals into output signals. And usually the input signals are going to be drawn from some class of signals that are OK to put through the system. And systems can take, we saw, continuous time input signals to continuous time output. They can take continuous time input to discrete time output, like, so they can process, say, continuous time inputs to continuous time outputs. And these things arise all the time. And you can have continuous time inputs to a discrete time output. And one kind of thing for this would be a sampler. I called it a T sub s sampler that takes x of t and gives you output signal, discrete time output signal y of n, where y of n for each n is equal to x at nts. So that's an example of something that takes continuous time input to discrete time output. Now, in both of these cases, actually over there I didn't elaborate, but here, this is assuming that x of t is a regular old, yes? Yeah, that's the one we were doing at the very end of class last time that I said class over because I forgot the formula. So but it was 12:55 to be fair, okay? You know, even 12:56 even. So we're going to do that in a minute. Yeah. Okay. So if x of t is a continuous valued signal, like a sinusoid or something, then so's y of n going to be continuous valued. So this could be either continuous or discrete valued, and y of n is going to have the same set of values. But we can also have something where you take a continuous valued signal and get a discrete valued signal. Okay, so in these pictures, these examples, the signals can be either continuous or discrete valued as opposed to continuous or discrete time. Okay, so like if x of t in this one is continuous valued, y of n is going to be continuous valued. But sometimes we have something like this. We have, say, a discrete time continuous valued x of n going into a system And what comes out is going to be a discrete time, discrete valued y of n. So this is discrete time, discrete valued. Now, what kind of a system would do this? Can anybody think of it? Think of something that might arise in applications. Takes a continuous valued thing and puts out a discrete valued thing. So if you want to think specifically real valued and then say bit string. Yeah?
ADCs?
Yeah, essentially a quantizer is what which is going to be part of an ADC. Okay, so an example of this would be a quantizer. So like in this case, we'd have y of n is equal to, say, q of x of n, where this is what the graph of q looks like versus x. Say it's going to be something like this. It's going to have various levels, like so. And this is just whatever. These are the possible values for y of n, the levels. And the same with these. And then you might want to encode these levels as bit strings. So there are 6 levels here. And there's a saturation level for the positive and a saturation level for the negative. There's only 6 of them, but 6 is not a power of 2. So we can't do exactly the number of bit strings equals the number of levels. So we'd have to go for 3-bit strings. Say you encode this one as 0, 0, 0, this one as 0, 0, 1, so on and so forth. You could do that. OK, so that's an example that comes up all the time, quantizers. Now let's talk about discrete time, continuous valued goes to continuous time, continuous valued. So how about discrete time, continuous valued inputs, and continuous time, continuous valued outputs. OK, so what is this kind of a system? This is sort of like the flip side of the sampler. OK, it's a sampler, assuming in this case we're talking about continuous valued things, takes a continuous time thing and spits out a discrete time thing that has the same value set as the continuous time thing. This one takes a discrete time thing and spits out a continuous time thing that has the same continuous value set as the input. OK, so what are examples of these? Examples of these are interpolators. And I want to talk about 2 different interpolators. And there's going to be a sort of a sacred special interpolator that we're going to encounter later in the course called an ideal interpolator. So what's an example of an interpolator? How about this one? First off, so one example is what we call the 0-order hold. Interpolator. What does this do? This takes x of n, input signal, and remember, this is going to have a t sub s associated with it, and gives you a y of t, a continuous time signal. And y of t is going to be equal to what? It's going to equal x of n when t is in the interval nts through n plus 1 ts. Now that looks kind of complicated. I hope everyone's familiar with this element of notation, right? You've seen that in your math classes, right? That just means that t lies in this half-open, half-closed interval. What is this doing? It's taking a discrete time input signal and putting out a staircase output signal y, whose stair heights are the values of the discrete time input signal. So y of t here, I'm going to draw a picture, is a staircase signal whose stair heights are the x of n values laid out in an appropriate way in time space. So for example, if x of n looks like this, say x of 0 equals 1, x of 1 equals 3, x of 2 equals, say, minus 1, x of 3 equals 7, then this is what y of t is going to look like, at least over the range 0 through 4. X of 0 equals 1, so y is going to equal this. X of 1 equals 3, so this is going to be TS. This is 3. X of 2 equals minus 1, so we're going to have a minus 1 down here. And x of 3 equals 7. So we're at 3 TS, we're going to go up to 7. So this is 7, 3, 1, minus 1. This is what y looks like over that range. Whenever t lies in between integer multiples of t sub s, this is 2t sub s, 3t sub s, y of t takes on the value of x at the n, where n ts is the left point of that interval. Everybody see what this is doing? OK, what's another kind of interpolator? So that's one example. This is the one I was doing at the very end of class last time. And by the way, why is this called an interpolator? It's called an interpolator because the signal y of t interpolates between the values of x and places the values of x at the integer multiples of t sub s. So you can think of this, there's a dot here, a dot here, a dot here, a dot here, and this is one way of interpolating between those dots. What's another way? If you saw a bunch of dots and you were a kid, how would you interpolate between them? Yeah. Yeah, straight lines. Unless you were like my brother, he would probably draw a catenary, whatever. But anyway, another example is this proposal. Another example is what's called a linear interpolator. And essentially what goes on here is that y of t, quote unquote, connects the dots in x of n, so that given by x of n, with straight lines. And the formula is going to be this. Signal x of n goes into the system, and this system has associated with it a parameter t sub s, the interpolation interval. And what comes out is going to be the signal y of t. And here's what it's going to be. It's going to be x of n plus t minus nts over ts times x of n plus 1 minus x of n. And this is when t is in that interval nts to n plus 1 ts. And this is the formula that I didn't put up last time because I forgot about the way I like to write it. There's various ways of writing this, some of which are better than others. Now, why do I like this way? Suppose I plug in little t equals nts. What do I get? Y of t equals x of n plus 0. So y of nts, so observe that y of nts equals x of n for all n because of the formula giving us y. And if you look at that formula, because it's linear in t, it has to be, y of t has to look like a line in between, a line as a function of t between its value at time nts and its value at time n plus 1 ts. So for the x's over there, for the x of n above, this is what y of t looks like, at least on the interval. By the way, this is the t-axis, and this is y of t. Starts off at 1, goes up to 3, goes down to, so this is a ts, goes down to -1, goes up to 7, like so. So this is going to be 3ts. This is going to be 2ts. Terrible graph. I'm not a good drawer. And this is 1, 3, -1, 7. OK? So that's another example of a discrete time input, continuous time output system. Both of these are interpolators. Now, not all such systems that have discrete time inputs and continuous time outputs are interpolators, but these ones are. OK, so anyway, I just want to do 2 more quickie examples because these connect to, you know, music and real life and everything a little bit before we move on. And one of them is like a CD audio set. Do you all know what a CD is? Yeah, I know. I mean, it's weird. I still listen to my music on CDs. Why? Well, where do I listen to music? I listen to music at home or in the car. I don't listen to music while I'm walking around campus, you know, and people say to me, oh, how can you deal? You know, my life needs a soundtrack. Well, my life has a soundtrack. It's like what people are doing and saying and the bells and people saying hi to me and whatever. And you guys are missing all that because of your AirPods, right? And there was actually a Cornell Sun op-ed last semester that said that AirPods are specifically designed to block out only half of the ambient sound so that you could participate in the ambient reality and listen to the music at the same time. Is that something you agree with or disagree with? Jordan, you agree emphatically? Yeah? What angle do you wear your AirPods? You know, all that kind of stuff. Anyway, I listen to CDs. And another reason I listen to CDs is because CDs are way better sounding than MP3s through any speaker system. Okay. Why are they way better sounding? You don't agree. You think I'm faking that I can tell a difference. You know, when CDs came out, all the vinyl audiophiles said, oh, well, vinyl sounds better. I can really hear the difference, you know. And the only difference I can hear is lots of ticks and pops and scratches on the vinyl, you know, an occasional turntable rumble. Oh, Alex, you think vinyl is better?
No, like I agree. You could tell a huge difference between very poor MP3s and CD quality. Nowadays, you can export an MP3 that sounds like pretty good, but that really depends on what you're using to export it.
Yeah, and it also depends. Whenever you use an adjective like good, you know, that's dangerous because it's a value-laden term. It's a eye of the beholder type of thing, right? Have to be careful with that. Nick, you?
If you listen to music with like WAV files.
You could do that, which are sort of like WAV files are less compressed than MP3. So, yeah, but let me just we're wasting time on all this chatter. Let's move along. How about the CD? So 2 more examples. And this is just to give you an idea of some numbers associated with the compression and the data rates and all that kind of stuff. So first of all, CD audio system. And I'm going to do this from front to back. So here you have your input signal x of t. So this is, for example, a music signal. What does that go through? That goes through an A to D converter. And this thing itself is going to be a composite of 2 systems. So this is A to D. So what's inside of here? What's inside here is a sampler. OK, so it's going to be a sampler. followed by a quantizer. And I know I'm writing a little bit small. And does anyone know what the T sub s for this sampler is? Remember, T sub s is, yeah,
44.2K.
44.1, actually. You're really close, yeah. Now, this is 44,100 hertz, or samples, or 1 over that is what T sub s is. So T sub s is equal to 1 over 44,100 because you take this many samples every second, so the interval between samples is 1 over that. Now, why that number? We're gonna talk a lot about this later in the semester, but anybody know why that number? Yeah?
It might have like a high enough compression rate that it saves a lot of data, but it's not high enough that you start to notice a difference.
That would be how I would explain it to my cousin, who's a sociologist. Okay, she also went to Cornell, by the way, class of 1955. She's actually my mom's cousin. So anyway, yeah.
Is it because it's a bit more than twice the human hearing?
Say again. I'm sorry.
Human hearing is like up to 20 kilohertz times 2.
Yeah. The audio signals have what's called a bandwidth of 20 kilohertz. That is to say, all the frequency content in audio signals, and the definition of frequency content in audio signal is what a human can hear. You know, these are not dog songs. These are human songs. And it turns out there's a theorem. There's a theorem in signal processing called the Shannon-Nyquist sampling theorem that says that as long as you sample a signal faster than twice its bandwidth, you can, in principle, recover the signal exactly from the samples. And that's one of those miraculous theorems, mathematical theorems, that comes into signals. And we're going to talk about that theorem later in the semester. So here, 44K is about twice 20K with a little extra for good measure. Okay, so that's why that's the T sub s. Now, and you may say, okay, well, so you put this through a quantizer. How many levels does the quantizer have? Does it look like this? Have just 6 levels? Well, it turns out this is a 16-bit quantizer. What does that mean? That means that I encode each level with a 16-bit string. That's a long bit string, and there's a lot of those. There are something like 65,000. I wrote it down, so where is it? 65,536 levels. So that's a really refined quantizer. Okay, so that's what happens at the front end of the CD audio system. And out of there, you get this signal. And I'm going to call it, well, we don't even have to call it anything. Well, I'll call it something, though. Q of n, say. And then you put these things onto a CD. So I'll call this Q1 of n. And this will be Q2 of n. And then you play it back through a CD player. And what that includes is things like, you know, an optical reader and a D to A converter, and you get Y of t. Okay? Y of t is not going to be exactly equal to X of t, but it's going to be close. So it's going to be close, not exactly equal to X of t. All right, so let's look at these two signals, Q1 of n and Q2 of n. These are discrete time, discrete valued signals, and figure out how many bits per second, what the data rate of those two signals is. And the first one is pretty easy. Second one, you're going to have to take my word for it. So the first one, what are the data rates in bits per second of the Qs here? Q1 of n All right, how do you get Q1 of n? You take, and remember we're talking stereo here, right? Two channels times 44,100 samples per second times whatever that 65 thing is, 65,530, is that what it is? Bits per sample. And that comes out to be something like 1,440,000, I forget what it is. 1,411,200 bits per second. And this is of just sampled music on the CD. Why is Q2 of n different from Q1 of n? Well, Q2 of n, so meanwhile, and you're going to have to take my word for this, Q2 of n contains lots more bits for things like track length, you know, like when you put a CD, now you may know what a CD is, but you may not know what a CD player is. My CD player at home, it tells me what track I'm on, how long I have left, how long the track is, all that kind of information. Now, what's your question?
So the second part of the AD is a 16-bit, right? So every time you make a sample, you encode that level in a 16-bit value.
Yes.
So why do we multiply by the 65,000 instead of 16?
16 bits is 2 to the 16th levels. Every level is encoded by a bit string. So what we have to do is we have to count up the number of 16-bit strings.
But each sample is only encoding one level, right? Because it's AD.
Yeah, maybe, let me just think about this. Oh yeah, 16 bits per sample, right. If you do this, this won't come out to, thank you, won't come out to be 16 bits per sample. Sorry about that. I wanted it to be a big number, but not that big. OK, so Q2 of n contains lots more bits. For example, track length, track number, control of various kinds, blah, blah, blah. And it turns out that it has, believe it or not, more than twice as many bits per second as Q1 of n because of all this junk. So it's kind of like junk DNA or something. So it turns out to be 2.94 megabits per second overall. So what does that mean for like a second of a CD, standard audio, is going to be about 3 meg. So a minute of CD audio is going to be that times 60, which is about 180 megabits. So thus, 1 minute of CD audio is roughly 180 megabits. All right. That's the CD standard. Now, what about the MP3 standard audio? And this one, the book actually has a picture. And by the way, this business about decomposing big, long, complicated systems into subsystems, we do that all the time. Yeah.
How do you distinguish between megabits and megabytes?
I'm being sloppy about that. Yeah. Like if I wanted to do megabytes, what I would do here, I would put 2 bytes per sample. So it would be a factor of 8. I mean, it's always a factor of 8, but yeah.
But when you do like capital S, capital B?
Oh, you mean symbol. I'm using a small b for bits. Yeah. Just trying to, I am being sloppy about bytes, bits, whatever. Just want to give you an idea of relative sizes in this particular example. OK. So meanwhile, consider the MP3, and I don't know how you like to write this. You know, it's one of those things. I always do dot MP3 just to be really pedantic. You know, like when I talk about PDF, I do dot PDF. Some people prefer cap PDF, all caps. What do you guys like? You don't mind. I can do it my way, and it's not going to bug you. You're not going to go tell your friends that the signals course is really pedantic about the MP3 being with a dot in front of it. Example from the book. And it looks an awful lot like that, except there's other stuff in there. And I just copied the picture out of the book. Essentially, you have your X to T, your music signal, same as in that picture over there. This goes into an A to D. And this guy is going to be the same as that one, you know, quantizer followed by, or sorry, the sampler followed by the quantizer. So this is same, say. And then it goes through an MP3 encoder. What does that do? I'll talk about that a little bit. And then you have the output of this is going to be your compressed audio file, which is, it's kind of like a data file, but you can also think of it as a, you know, how many bits per second. Then it goes through an MP3 decoder. And then it goes through the D to A, and you get your output Y of T. As before, and it's going to be a different Y of T from that one. And the D to A in there, you know, and in between the D to A and Y of T maybe are going to be your AirPods, right? So there's yet another piece of equipment in there. But anyway, what does the MP3 encoder do? This is we've already seen, this is a huge data rate sample, 1,411,200 bits per second coming out of this. And what is the data rate of this signal going to be? Does anybody know the ballpark on that? You're not allowed to answer the question yet. There was a reason that I calculated what 1 minute of CD audio roughly was. Yeah.
Around a good MP3 is around a fourth uncompressed. So
Well, I've heard, this is what I've heard on the street. That, no, that, like, not even on Hope Plaza. This is on the sort of the more seedier streets of the west end of Ithaca. Is that a minute of music is about a meg of MP3. That's not a factor of 4. That's more of a factor of, maybe with bytes. I don't know. But roughly speaking, this is going to be like 1 megabit per minute, which is the same as how many megabits per second? You know, 1/60th of a megabit per second, which is a lot less than that. Now, what were you going to say, Alex?
I was about to say, like about 128 to 320 kilobits per second. So.
Can you do the math in that and get a meg like?
Yep.
Any savants in? What's that?
I don't have a calculator.
Bummer. Okay, I have my phone, but I don't want to waste time on that. So. Okay, so I'll put I think. At least that's the rumor I've heard. Okay, so it's a lot less. And you may say, well, how in the world can you get the quality that I get from my, you know, listening to my AirPods playing an MP3 with that much compression? How does that work? So clearly, lots of compression happening here. How does quality persist? Well, I think this is pretty easy to explain, to tell you the truth. It turns out that the kind of compression that MP3 uses is based, at least in part, a large part, on the idea of wavelets. Okay, so the kind of compression here, it turns out wavelets play a role. And to explain roughly, you know, to explain to my mom's cousin for example, how this might work. Think of the following example. Like, think of a German flag. Anyone know what a German flag looks like? It's like 3 horizontal stripes. It goes black, yellow, red. Okay. Now, suppose you had a digital image of a German flag. Say it had 4 megapixels, right? And we talked about color images last time. How would you describe the German flag? Well, you could you could make a list of 4 million bit string triples for red, yellow, and blue for each pixel of that flag, right? That would be one way to do it, if I have a 4 megapixel picture of a German flag. But obviously, the German flag is just 3 stripes, disjoint from each other, each of which is 1 color, right? So what's a better way to describe the German flag? You say it's 3 stripes, and the black one goes from here to here, and the yellow one goes from here to here, and the red one goes from here to here. Now, that's a much shorter description than 4 million lines of whatever. So it turns out that wavelets enable you to do that kind of thing with other kinds of signals. And essentially, like if you're listening to music and there's a note that persists for a long time, instead of saying, you know, C sharp, C sharp, C sharp, C sharp, C sharp, C sharp, C, try to do that fast. Oh, E flat, that's much easier. E flat, E flat, E flat, E flat, E flat, E flat, E flat. And by the way, Alex has perfect pitch. So he's going to help us out when we bring the keyboard in and whatever. Tell us when it's out of tune. Anyway, you don't encode the music that way. You say, OK, it's E flat starting here until here. That's a much easier way of describing that piece of music. And that's the kind of compression that occurs here. So think here of describing, say, a color field image. And you know, there's some painters that do these things, like Mark Rothko is one famous one, or a German flag. And there's plenty of flags around the world, like that are 3 stripes. You know, Russia, France, Italy, Ireland. You know, all those are just color field images. You do this not by listing every pixel, but instead by just giving a description of what's going on in the picture. And the same thing works with sound in this way. So those are 2 examples from everyday life that you'll see. And give you an idea of signals. There's discrete time, discrete valued, continuous time, continuous valued, continuous time, discrete valued, blah, blah, blah. There's quantizers, there's samplers, there's interpolators, there's everything. So, you know, breaking these things into pieces, that's what engineers do, and they design the pieces individually and so on. OK, so now's a good time. Remember I said we were going to take a 3-minute break during the class in general. So now's a good time for the 3-minute break. And those of you who are sleeping can wake up, go have a donut or something, and we'll continue in a minute. OK, so now on to sort of chapter 2. The title of chapter 2, I think, is just sinusoids. I think that's what the chapter is called. And we're going to be talking about sinusoids, etc. And when I say etc., I mean we're going to talk about general periodic signals a little bit. We're going to talk about you know, spectra. What do we mean by a spectrum of a linear combo, finite linear combo of sinusoids, etc. Anyway, so this is where we really get mathy. OK, so we're going to be spending a lot of our time for now for the next little while on continuous time, continuous valued signals. So none of these bit strings or anything like that, or quantized things, but continuous time, continuous valued signals. And the typical notation is going to be like I've been writing. Things like x of t, y of t, etc. The little t, remember, always represents a continuous time variable. And the continuous time, continuous valued signals are going to be either real or complex value. But for now, let's just talk about real valued. So for now, let's consider only real valued such signals. So not complex. Because I want you to contrast here real versus complex as opposed to real versus bit string. You know, that's what. OK, so what about these things? It pays sometimes to think globally, to think big, not to think about individual signals, but to think of whole sets of signals. So say I'm given such a signal, x of t. What can I do with it? Well, one really elementary thing I can do with it is shift it. So if I'm given such a signal x of t and some real number, let's call it t0, we can form another signal, y of t, by giving y of t the following specification. Y of t equals x of t minus t0. This is just a time shift of the signal x of t. So y of t is, quote unquote, and is this elevation of the lower bound sufficient, folks? Good? We good? That's what we say in New Jersey. I grew up in New Jersey. You say, we good? We good? That means many things. Have you seen that meme? Yeah, that's a good one. OK. It can mean like 7 different things. It can mean like you know, are you still my friend? Or why did you just bump into me? You know, it can mean all kinds of stuff. You know, we good? You know. All right. So y of t is a time shift by t0 of x of t. So suppose you graph x of t versus t. You can always do that. So for example, if this is what x of t looks like versus t, see my generic signal, something like that. And what if, say, t0 is positive? So x of t minus, say, 3. And suppose this is time 0. This is time 1, 2, 3. What is y of t going to look like? Is it going to look like this graph shifted to the right, or this graph shifted to the left? How many people think right? How many people think left? OK, lots of abstentions, but no wrongs. OK, unless you're secretly harboring to the left. You're hesitating about something. Right is right. OK, this is shifted to the right by 3. So whatever happens at time 0 is now going to be happening at time 3. So it's going to look like this. And then it's going to go blah, like so. So x of t, quote unquote, x of t shifted right by 3. And similarly, if t0 happens to be negative, you shift by absolute value of t0 to the left. Right? So that's one thing. And the way I would summarize that is by saying, if you take a signal and shift it, you get another signal. And a way that an applied mathematician might describe that is that, remember, I'm trying to encourage you to think big, think about sets of signals. An applied mathematician would say, the set of all continuous time real valued signals is well, it's infinite for sure. It's closed under time shifting. Anybody hear that kind of talk? You've heard that before, right? Yes. Somewhere. Maybe even from Al Monar, who knows? You know. So the set of all, thinking big, thinking globally, quote, the set of all continuous time, so real valued, continuous time signals is closed under time shifting. If you take one and time shift it, you get another one. Okay, so what are some other things you can do with signals? Suppose you have two continuous time real valued signals, say x1 of t and x2 of t. So next, if I'm given two such signals, x1 of t and x2 of t, what could I do with them? I could make another signal in many different ways. Just tell me one easy way to make another signal out of those two. Yeah.
Add them together.
Add them together. That's one.
Add their shifts together.
Add their shifts together. You could even multiply them, you know, but we're not going to worry about that so much for now. But one thing you can definitely do, and this is a generalization of adding together, is taking linear combos of them. So if you're given two such signals, x1 of t and x2 of t, and real numbers, C1 and C2, we can form a new signal, y of t, by, for each t, taking C1 x1 of t plus C2 x2 of t and adding them together to get the value of y of t. Right? And we can extend that to any finite number of signals, x1, x2, x3, up to xn. You can take a linear combination of them with real coefficients and get another signal. OK, so that is to say, quote unquote, the set of signals, and I'm abbreviating real value continuous time signals with just the word signals, is closed under taking real linear combos. Okay, now does anyone remember? I mean, theoretically, there's a certain course that I'm referring to without naming that's not a prerequisite for this class. But those of you who've taken it or who even took a course sort of that touched on the stuff in high school, you know what we call places where you can take linear combos. What's a name for a place where you can take linear combos? Yeah, a vector space. The set of all real value continuous time signals forms a vector space over the reals. So that's, I'll give you like a technical statement. I guess I have to do this here. So technically, this set of signals is a vector space over the reals. That's how you would describe it in mathematical terminology. That's closed under time shifting. Okay, so that's, by the way, the book doesn't talk about this global thinking stuff so much, but I think it's a good thing to do, just so you back off and think of the big picture once in a while. Okay, so set of all real value continuous time signals is closed under time shifting, and it's a vector space, forms a vector space. Now there's lots of different examples of real value continuous time signals, right? And we're going to be talking in depth about the sinusoids and linear combinations thereof. But first, I want to talk about the general notion of a periodic continuous time signal. Okay. So if I'm given a continuous time, continuous valued signal, and I'll just say signal for now, x of t, we say that x of t is periodic when there exists some cap t bigger than 0 such that when I shift x by t using time shifting, I get x of t back. So x of t minus cap t equals x of t. That is to say, shift x of t by cap t implies you get the same x of t back. So the periodic signals are the ones that are fixed points of some time shift operator for a positive cap t, if you want to talk mathematically. Now, by this definition, how about the signal x of t equals 3 for all t? Is that periodic by this definition? How about any constant, any real valued constant valued signal? 0, is the 0 signal periodic? Yeah? How many people? Let's vote. Like, technically, by this definition as written here, is the 0 signal periodic? You have to go yes. Yes or no? Yes? No? OK, well, you're right. By this definition, it is. Because you could go out on Ho Plaza and say, just shout at the top of your lungs, give me some t bigger than 0, and the first answer that comes back to you works in this definition. For the 0 signal, if I have x of t as the 0 signal, and I shift it by 7, or I shift it by 13, or 19, or any of those numbers, pi, I get the 0 signal back. So every constant signal x of t, including the 0 signal, and of course that's obviously a special signal, and any vector space has to have a 0 vector, and the 0 signal is the 0 vector in the vector space of continuous time real valued signals, is periodic. In fact, any positive t works in the definition to verify periodicity of such a thing. Okay. But if x of t is not constant, okay, and is periodic, so if x of t is not constant but is periodic, it turns out that unless x of t is really pathological, and I will give you examples of such pathology, just so you'll believe me that it's not a universal thing here, then provided x of t is a decent kind of signal, if x of t is reasonable, it's not going to be true that any t bigger than 0 works in the definition. In fact, it's not even going to be true that arbitrarily small t's work. There's going to be a smallest t that works in the definition. So there will be a smallest t bigger than 0 that works in the definition. Of periodicity. And we call that t0 the fundamental period. So we call that t0 the fundamental period. Of x of t. And we're going to do some examples in a sec. Anyway, and what is the fundamental frequency, assuming that t0 is in seconds? The fundamental frequency, which we're going to call f0, equals 1 over t0. And this is going to be in Hertz, abbreviated Hz. This is x of t's fundamental frequency. Now, Hertz is kind of a weird word, I always thought. You know, it's Heinrich Hertz, named after Heinrich Hertz, but it sounds like a plural, even though it's a name, a proper name. And so, like, when I was a kid, you know, in New Jersey, like I said, you know, we had, and you'll hear about this a few times, we had TV, it was broadcast TV. There was no such thing as cable TV, right? And we had channels coming from New York City, right? And we had 2, 4, 5, 7, 9, 11, and 13, and the other ones didn't work. So there were a limited number of channels. And back then, channels didn't go 24/7. They signed off. And so like at 2 a.m. or whatever, when they signed off, there would be like a test pattern, and there would be this voice would say, this is station WNEW, New York, operating at a frequency of whatever it was, megahertz. Okay, now when you're a kid, you know, like an 8-year-old kid, and you hear some guy on TV say, so many megahertz. What does that sound like? Doesn't that sound like a really painful kind of thing to undergo? I mean, you've sort of heard the word mega means big somehow, and hertz, you know, it just sounds like that. So I always visualized this as mega H-U-R-T-S when I was younger, and not until I went to school, university in fact, did I learn it was named after a guy, Heinrich Hertz. But anyway, time, t0 is always going to have dimension of time and units of seconds. f0 has dimensions of inverse time and units of hertz. There's another way we describe frequencies sometimes. So sometimes we describe frequency using different units. Different units from megahertz or whatever. And does anyone know what those units are that we sometimes use to describe frequency? It's just off by a factor of something from Hertz. Okay, radians per second. Radians per second is equal to 2 pi times Hertz. And we talk about the angular frequency of one of these signals is going to be like little omega 0. So for a signal x of t with fundamental period t0, its fundamental angular frequency is little omega 0 equals 2 pi over t0 radians per second. And moving back and forth between omegas and f's is something that, you know, it's not that much fun, but it's something you should be able to do with great facility. OK, now let me just back up here. And remember I said if x of t is not constant but is periodic, it has a fundamental period, provided it's reasonable. What's an unreasonable signal? What's a periodic, non-constant periodic signal that has no fundamental period? What does it mean to have no fundamental period? It means that it has arbitrarily small periods. If every t in the definition of periodic is a period of x of t, so that's a piece of terminology. So when x of t is periodic, any t such that x of t shifted by that cap t is x of t all over again is called a period, indefinite article of x of t. And so the fundamental period is the smallest period of x of t when x of t has one. So when x of t is reasonable and not constant, and periodic, the fundamental period of x of t is just the smallest period of x of t. What is an unreasonable signal that has no smallest period? So here's an unreasonable x of t. X of t equals when t is a rational number and 0 when t is irrational. And I'm assuming everybody knows what rational and irrational mean. Rational number is just a fraction, ratio of integers. Irrational number is anything that you can't write as a ratio of integers. Examples of irrational numbers that occur in daily life are square root of 2, okay, pi, e, those are even more irrational than the square root of 2. They're what we call transcendental numbers. But anyway, okay, so first off, why is this signal periodic? What are its periods? Two is a period of it. 3 is a period of it. Why? Because when I shift x of t by any integer, in fact, by any rational number, all the rational numbers shift to other rational numbers, all the irrational numbers shift to irrational numbers, and therefore x of t stays the same. So observe that every positive rational number t is a period of x of t, in the sense that if I shift x by such a t, cap T, I get x back. Since there's no smallest positive rational number, there's no smallest period. So no smallest positive rational number implies no smallest period. And even aside from the fact that this x of t is periodic and has no smallest period, I think it's about as unreasonable a signal as you can get, for obvious reasons. Like, it doesn't even have jumps, right? It's that bad, it's that bad a signal. But anyway, that's just to make sure you believe that such a thing exists. All right, so we could go on and think globally. Like, for example, if I take two periodic signals, two non-constant periodic signals, x1 of t and x2 of t, take a linear combo of them, do I get a periodic signal? How many people think so? Linear combo of two periodic signals is periodic. Okay, how many people think maybe and not necessarily? Clearly, it's true sometimes. Why do you think maybe not? What might happen? You were the one who raised your hand, so you must have a reason.
I was thinking about like when you take a linear combination of like several columns of a matrix or something like that, you don't necessarily get like a scalar multiple or something of the original column.
That's a really good way to think about signals as vectors. Congratulations. But most people at this level don't think about signals that way, as analogous to vectors or whatever. But it's true. That's true. But it turns out that it's not necessarily true, and we're going to see that as we go along. That in some sense the signals have to be in sync. Their periods don't have to be the same, but they have to have a rational ratio. One has to be a rational number times the other one for every linear combo of the two signals to be periodic. But anyway, okay, so we'll move on to that as we go along. So last thing for today, what are the elementary particle quarks of the periodic signal universe? Quote unquote, elementary particles of the periodic signal universe are pure sinusoids. Okay, so what's a pure sinusoid? A pure sinusoid is just going to be something that looks like this versus t. Going to look like this. And actually, I'm not even going to put where t equals 0 is. It just looks like that. And I'm drawing terribly, as always. 0 can be anywhere. That's what I mean by a pure sine wave. And we're going to talk about those, like the amplitude, what's the fundamental frequency, what's the fundamental period, and depending on where 0 is, what's the phase, all that. We're going to continue with that next time. So see you Tuesday.